Welcome to question 6 from Chapter 2, the Fundamentals of Particle Technology book. We have here a lot of information in question 6, and I can see that I'm slightly obscuring some of the information. That doesn't matter too much, but let me try and explain what we're doing here. We have essentially a problem, and the information that we've been given that is most relevant to the problem is just here, which is really part 1 of the question. Okay, and in part 1 of the question it talks about having a cumulative size distribution, powdered material that may be represented as a straight line on a percentage number undersize versus particle diameter graph passing through the points 0% by number at 1 microns and 100% by number at 101 microns. And then there are 4 options for what the equation for n0x is. So by inspection of the graph, the intention is to come up with the correct value for that equation in part 1. Well, the ultimate objective, if I scroll right the way down to the bottom, is here. The ultimate objective is this. Basically to calculate the specific surface area per unit volume of this material that has the size distribution that's just been mentioned, and there's this additional factor thrown into the mix about sphericity, but we'll tackle that later. So the essential question is what's in part 7, as I've just circled here, and all the intermediate parts are really parts that are part of the problem decomposition to get us from the initial statement of fact to the real, actual, interesting result that we're after. Okay, I think I need to set the scene a little bit. I want to leave a bit of space for some calculations. So let's set the scene down here. And this sort of thing is what we were discussing in the previous questions. It's about the distributions. And a cumulative number distribution would look something like this. We're using n0 for cumulative, capital N0 or uppercase N0 for cumulative number, and that's against particle size. We're using x for particle diameter, okay, not d, otherwise we'll end up with too many d's when we start to do differentials, and that goes up to 1.0. We don't use percentages when we're doing calculations. As it happens in our particular example here, we're talking about something that goes between 1 and 101 microns, but let's not worry about that for the moment. I'm more interested in the general principle. And the general principle is that we have a cumulative distribution looking something like this, and if we know what that function is, what the equation is for the cumulative distribution, then we can differentiate it. Okay, and that gives us the number lowercase, which is going to be the differential curve, the relative number per micron range curve, which will look something like that. So we can obtain the equation, or the function if you like, for the relative number per micron range by differentiating the cumulative curve. The area under this equation here, sorry, this curve here, is n0x dx equal to 1, or 1.0 as I've drawn up here. Okay, so that goes up to 1.0, and that's a consequence of this integration just here. There is a bigger picture. Why do we bother doing this? In what practical use is there for what I've just described here? If we know the relative number per micron range functionality, then we can use it to calculate a whole host of things, because pressure drop, for example, is proportional to, I was going to say equals, but that's probably not a good idea. It's proportional to some function, so I'm using f here as a function rather than frequency of particles, but it's a function of n naught x. Sorry about the messages. N naught x dx. Reactivity, or some degree of flux, again, is a function of n naught x dx. So if we know what that equation is, then it enables us to calculate the pressure drop, the reactivity or flux, mass flux of something, or possibly even some scattering parameter, maybe light scattering parameter or light absorption for solar cells. You get the idea. It's the same sort of thing again. So if we know what this equation is for this material, then we can then go to our design equations or control equations, or simply equations that help us understand the process and see what the effect of changing the size is on some of these outputs. So that's what we're trying to do. So we're trying to be able to predict the performance of our particles from a knowledge of their particle size distribution. Okay then, so let's try and answer this question as best we can. This question says the cumulative distribution, so we're going to go from 0 to 1, 1.0, and this is our cumulative distribution n naught x of that axis, particle size along this axis. We're going to go from 1 micron to 101 microns. So that's 1 to 101. And it's a straight line. Looking something like that then. Maybe that's 101. Okay, so by inspection, we know that it's the change in y value divided by the change in x value. In other words, we're talking about an equation of a straight line, y equals mx plus c, and that change in y value is from 0 to 1. The change in x value is from 1 to 101. So we have the equation that should be answer C. If you put in 101 there, you get 1.01 minus that value there gives you a value of n naught x of 1.00. If you put in 1, then that's 0.01 minus 0.01 gives you a value of 0. So it gives us our correct limits, and it's got the right delta y values. So that, by inspection, is our equation for n big uppercase n naught x. Now we need to differentiate that to get the lowercase n naught x. That's nice and straightforward because we just drop the x. So that is our equation for little n naught x, lowercase n naught x. Let's have a look at what that looks like, and if we can see anything more about that. So what does little n naught x look like? I'll come back over here, I think. So little n naught x looks something like this. We're now talking lowercase n naught x. Has a value, minimum value of 1, maximum value of 101. And it's a constant. 1 over 100. It's a constant. So we're at that value of 1 over 100. Okay? Important point here is that area. I think you can see quite easily that if we integrate n naught x dx between 1 and 101, clearly that gives us an area of 1, as it should do, because that's what we sum up to in the cumulative curve. The maximum value is 1.00, and that should always be the area under the curve. And we have 1 over 100 here, multiplied by 100 here, so we're going to get unity. So what's the shape of the n naught x given in part 2? Well, that's the shape of it. And what's the significance of that shape? It helps to confirm our statement about the integration and differentiation. The next question, I've dropped the question a little bit here on pulling it around. The next question really is what equation is the best equation to use. I'm going to have to try and take that back up a little bit, I think, because that's better. Okay, it says here, what's the best equation to use for calculation of specific surface? If we scroll down a little bit, the equations for specific surface are here. This is for the number distribution. Okay, so we need to calculate x squared and x cubed as functions. Here are our shape factors. We're assuming spheres, so the surface area of the sphere is pi times by the diameter squared. The volume is pi over 6 times by the diameter cubed. So here is our basic equation for specific surface area per unit volume as a function of little n naught x, which is the number distribution. So if we come back to our options for this particular question, the best equation to use for calculation of specific surface. Well, we've just worked out that that is the function n naught x. So we're just putting n naught x into our equation. So we've got x squared n naught x dx. So that is technically correct, but the question is asking something relevant to engineering, really. What's the best equation to use? N naught 1 over 100 is obviously a constant, can be taken out of the integration and cancelled out. So the best equation to use is actually this one down here. There's less chance of making a mistake because we've simplified the equation. We can't cancel any x's, but we can certainly take constants out of the integration and then cancel them out. So this is now what we need to calculate. And I think probably best to come over to a different colour and we'll try and calculate it above where we've created a bit of space. So SV is equal to 6, and then we have the integral of x squared. Well, that's obviously going to become x to the power 3, but we'll also have to divide by 3. Okay, so that will integrate to that with the limits of 1 to 101. And then we're over something that we're going to have to divide by 4 as part of the integration. But it's the same principle, we're just adding 1 to the power in the usual integration way. So that's going to integrate to x to the power 4, 1 to 101. Okay, which we can simplify a little bit, although I'm desperately getting close to running out of space. We can simplify a little bit because we can bring that 4 to the top, so that becomes 24 divided by 3, which is 8. So that becomes 8 just there. And then we have on the top, if we just bring this down a little bit, it'll give us some space back. That's good. So we have 101 cubed minus 1 divided by 101 to the power 4 minus 1. That's what our specific surface area per unit volume will be, which I've actually plugged into Excel because it just makes life easier to use Excel rather than a calculator when using such large numbers. So that is the 101 cubed, that is the 101 to the power 4. That's taking 1 away from those values, and then that's multiplying by 8, or 24 over 3, which is 8. So we get the value of 0.079. So if we just close that down again, don't want to save it. So 0.079. Okay. So specific surface area per unit volume for this distribution is answer D, 0.079. The conversion to one with SI units is simply to convert it to meters to the -1. So that's 7.9 times 10 to the 4 meters to the -1. Fine particles have very large surface areas per unit volume, and remember, the easy way of remembering this is if we were converting that from microns to meters, we'd be dividing by 10 to the 6, but we multiply by 10 to the 6 because we're talking about microns to the -1. Okay, so that is our SI unit of meters to the -1, the specific surface area per unit volume of this material. The final trick here, or the final test here, is the sphericity. And a sphere is an object that has the minimum surface area per unit volume. So what we need to do with this is to divide by the sphericity, because the surface area per unit volume can only go up. So if we're dividing, I guess we're back to microns again. If we're dividing 0.079 by 0.9, that gives us a value of, let's check it on the calculator, 0.079 divided by 0.9 is indeed 0.88. given the answers that were available, it could have only just have been that one. So that becomes our final answer to the question. If we scroll back up to the top, okay, we have this distribution, a straight line, which we've looked at just here, although I've lost the graph on it. So we have this distribution, and that distribution, gives us a specific surface area per unit volume of 0.088 microns to the -1. Okay, that's it. Goodbye.